has been effective so far. At this moment, we do not want to waste time. Let me call upon our facilitators, Dr. Helen Namaweje and Professor Balaba. Dr. Namaweje, over to you.
Thank you so much, Dr. Nyararo. I think there is an echo. A very good morning to everyone. Welcome to day 5. I'm glad that we are generating on well as we are pushing on with data analysis and getting to know more on how we can analyze our data. I welcome you all, and I want to confirm in the chat if you can hear me very well. Can you hear me? No. Yes, they're saying yes. Okay, now let's get started. I sent some work today. I don't know whether you really managed to get some little time to go through in the data set that I sent on salaries, whereby I asked if you can create a simple linear regression and then a multiple linear regression, and also be able to explain the result. If the people who have tried, I'll be happy to see through what you've done. And if there is no one, I'll still go ahead and walk through with you. I'm seeing God. Samuel, yes, Samuel would want to present. Morning, David. We have a small exercise we want to have with the participants. Just maybe you can get 2 participants to present on simple and multiple linear regression. Kindly give them give some of the rights to share. David.
Yes, we are promoting them.
Thank you. Anyone who wants to present? If you've tried out something.
Only one participant has raised their hand.
Okay, we can have that one. Okay. And in case you try to do the work that I sent and you're willing to present, feel free to share with us and then we'll see what you've done.
Godwin, please go ahead.
Godwin is muted.
Yes, hello.
Hello.
Yes, instead of using my phone I'm now logging with my laptop so that I can share on my laptop. Currently, you just allowed me on my phone. So, okay.
Okay, as we give some few minutes to Godwin to get to his computer, is there anybody else who is willing to present? One person?
Please raise your hands and then I promote you.
In case there is somebody interested to present apart from Godwin, kindly raise your hand such that you're promoted.
Okay, I'm in now.
Okay, get started.
Okay.
Please, can you see my screen?
Not yet. Yes, it has started sharing.
Okay.
So I didn't finish. I just saw the exercise this morning and I started trying it.
Mm.
So what happened was, first of all, I tried to load these packages, my R script, and then after that I went ahead to create my object called salary. Please, can you see my cursor?
Yes, we can see what you're doing. Please take us through.
Yes, and then I set my working directory by going to session and then using that automatic method of creating the directory. And then I imported my data set named salaries. And I will just run it for you to see. After which I tried to check the nature of my the first six rows of my data set. And as you can see at the console, this was how the data looked like. So I went ahead to check the structure as well. And in the structure, the rank was a character, and discipline was as well a character. So I tried to change our discipline to a factor and also rank as a factor. So I'll just run that. And then I went ahead to view the characteristics of the data by running a scatter plot with this command.
Excuse me, Godwin.
Yes.
Can you mute one of the gadgets you are using?
Sorry. Yes.
Please go ahead.
Okay. So this was the function I used for the scatter plot, where my x was the salary. That is I think the dependent variable, and y was my independent, which was the years per service. And then here it meant that salary is a function of years of service. So I ran it. And then at my extreme, right, you can see the nature of my scatter plot. And with this one, I didn't know how to interpret, but then it's as if the data was normally distributed. I don't know whether that interpretation was right, but it's like there's some even distribution of the data set points. So I will do that and then go ahead to run my linear regression. And here again, I use salary as a function of years of service. And the data set was salary. So after running it, this was my intercept was 9,997. No, 99,974.7. And then I went ahead to check for the summary. Yeah, so you can see that I had over here my intercept was a positive intercept, and the years of service was 77. No, the salary a unit increase in the years of service will increase salary by 779.6 units. So this was where I got to, and I don't know whether the procedure was okay.
Okay, yeah, that is so great. Thank you so much, Godwin, for trying to do the assignment. And did you do the one of multiple, or you just stopped there?
I stopped there because I just checked my mail and I saw this.
Okay.
So I started doing it until
thanks for the great work. When we move on to the command scatter.smooth. Are you seeing it on that particular line?
Yes, scatter
Yes,
smooth,
here.
yes. Yes.
Look at it again. Don't you think that you mix something when it comes to X and Y, what you fit? What was your dependent and what was?
Yes, over here, I made a mistake. The salary, I think, is a dependent variable.
Yes.
Yes, I made a mistake there.
Yeah, so you need to switch them. The Y should be salary, and then the years of service should be your X.
Okay.
Okay, fine. That is great. Thanks for trying. That was great because as you keep on trying, we get to understand more on what is happening. So far, so good. That is what Godwin has shared. It's great work. He only did the part of simple linear regression. And so with the data set that I sent, it's a salaries data set and has got different components, the years of service, the ranks, and then so we are going to go into more details, but I'm just wondering if there is somebody else also wants to present. Godwin, thank you so much for trying and representing the rest of the group. Do we have one more person? I saw somebody who had raised their hand. Anyone who wants to present, or we continue?
I promoted Wycliffe.
Okay.
Yeah.
Thank you. Wycliffe, can you share with us? Hello, Wycliffe, you're waiting for you to share with us and then we proceed.
He's not taking up the offer to be panelists. So maybe you could move on.
Okay, fine. Now, what I'm going to do today, we are having a conclusion on both the linear and then the multiple linear regression. So what we are going to do, well, Wycliffe is saying that he's having a challenge with the connection. Okay, it's fine. Let's proceed. Like I told you, I sent an exercise whereby it is a salaries data set. And among the different variables we had rank, which had 3 variables. Within this rank, we had with the 3 levels, associate prof, assistant prof, and then professor. It had also discipline as a variable, which we had variable A and B. You can consider maybe A to be arts and then B to be sciences. We had the sex for male and female, then years of service. I mean, that is the experience. You can talk like that. Then salary, and then the years since PhD. So that is the data set that I sent. And I thought maybe you can try to practice and then share with us and see how far you've gone. So I'm going to share my R, and then we'll quickly go through it, and then I move on to something else. This is just a recap of what we did yesterday. Okay. Yes, hope you're seeing my screen clearly well. It is the exercise that I sent, salaries data set. I've talked about the variables. We are going to do just a simple exercise. We are going to run a simple linear regression when we are considering a continuous variable. The main inch for today, where I want to put more explanation, is when we are having a categorical variable. And then, of course, the moment you understand the simple with the continuous, and then a simple with a categorical, it implies that you are able to understand in case all the variables are combined together. So what I'm going to do, I didn't send this data set for you because I wanted you to manipulate your own to show me how you can, load the libraries, then import the data in R, and also show me how you can get the simple linear regression and the multiple linear regression. So don't ask for this data set. It was an exercise for you to manipulate from already the existing data sets that you have, especially the one that I sent on linear regression. But let's take through. It is just an exercise that I sent. So the first thing that I did, I loaded my libraries because they're already installed on my computer. Okay. Now I went ahead to set my working directorate. Like I said earlier, there are various options on how you can load your data, depending on what is easy for you. I believe at this particular point in time, we all know how to create, to set a working directorate. So I called my data set salaries, which is salaries.csv, which I want to import in R. Okay. The moment I see that whatever I'm running in the R studio, it is running in the R console, then I'm confident that whatever that I'm doing, it is okay. Sorry? I zoom in. Okay. I'm told that I zoom in. Okay. How about there? Are the words clear now? Okay. Hope you can see the words now. Okay, fine. So what I did, I imported my data set salaries with the read.csv command. So after loading my data set, the next step, sometimes it's always good to get familiar with your data set. I wanted to find out the structure. When I check in the R console, it is telling me that I've got 397 observations in that data set and 6 variables. And among the 6 variables, I've got rank, discipline, years since PhD, years of service, sex, and then salary. However, when you look at the structure, we've got whereby rank is a character, discipline is a character, then sex. But then when we know that these are categorical values, remember the next thing that we need to do is to tell R that these are categorical variables. Okay, because I'm going to use them. All I'm going to do is to highlight this part, everything, all the categorical variables, just to alert R that look at them as categoricals, which was rank, discipline, sex, and then the rank. To confirm that, I can run again the structure and see whether that I've told R to do has been successful. So it will tell where there was character, you can see that it has been changed to a factor. Okay. Sometimes in case you're interested in running the tables, it's still okay. You can run a table for salaries and then discipline. Just in this particular case, all you need to know is how many are those in discipline A, and then how many are those in discipline B. So when you look in your R console, the ones in discipline A are 181, and then in discipline B, they are 216. You can also check for the case of the rank. You can also check in the case of what? In the case of sex. All right. Now, since I'm going to perform a simple linear regression and then a multiple linear regression, sometimes when it comes to categorical variables, for example, the one of rank, where we are having associate professor, assistant professor, and then professor. Sometimes when you can tell R to give you a reference level among these categories. It does, because you don't tell it, it does it automatically. What? I've done it. No? They're asking for it? Okay, like I mentioned earlier, that what I'm going through was the exercise I sent. So I expected you to manipulate the codes now on your own. That's why I didn't send this script. But try to follow, and then later I can send it after. But it's also good that you practice on your own. Okay, what I was saying that sometimes in case when it comes to categorical variables, sometimes you might want to create, in case you're explaining the different levels, you might want to create a reference category. For example, we want to explain salaries in terms of the rank that we are given. The rank has got 3 levels. It has got the associate professor, assistant professor, and then professor. So in case we want to explain how the salaries vary in these particular categories, we need a reference within the 4 levels that we have. So R gives you an option and asks you that, okay, which one would you want to make your reference category? Or you can just let R to decide for you and you don't put a reference category. But sometimes why we put a reference category is to support the argument that we want to put across, especially as far as our objectives are concerned. Okay, so now what I do in this particular case, I come here, okay, on what I have highlighted. I say that when you look, I'm putting salaries again, okay? That within my salary data set, okay? This pipe, we said it's a connector. Go and pick the variable rank and then relevel it. When the moment within rank, I want to relevel such that I consider assistant prof as my reference category. That's what the ref implies here. REF in the 3 categories that I have, ref, I'm going to be explaining my results in reference to assistant prof. So that is why, okay, that's why I've got that particular line. So what I'm going to do, I run it. The moment I run it implies that this time around, I've told R not to do the reference level for me. I've just commanded it that do it for assistant prof, because with R, it can pick any level among the categories that you have. So when I move on, and then now I'm moving to the exercise that I gave you, a simple linear regression. I told you that consider salary as the dependent variable. We know that we use an LM, which is our command. LM inside, you put the dependent variable as a function of a Y variable. In this particular case, I considered my Y variable because I told you choose any. For a case of simple, we only consider one variable. So you're only supposed to choose only one. Okay, I considered years of service. I wanted to see, is there any relationship between salary and the years of service a professor's work, the different categories of with the different experience that is there? Could there be any relationship with the years of service that somebody has worked for in relation to price? So that is what it means. I ran that line, and then I want to see the summary of the result. This is what Godwin has just shown, which is very good. And we are coming up with similar results, and that is wonderful. And the way we've been explaining our results most of the time, yesterday I talked about the null hypothesis, whereby it is whereby you're committing type 1 error, okay? The probability that your alpha is equal to 0.05 or our level of significance. Now, when it comes here, you see that I'm only going to explain about the key important things because I looked at most of the things yesterday. What I am more interested in are the coefficients, okay? I see that I'm given my intercept, which is a 99974.7. I'm given the standard error, the t-value, and then the probability, the probabilities. But kindly note that the results that we are having here are got from the data set, the data set salaries, okay? So when it comes to the year.service, the years of service, we are told that the estimate, it is 779.6, and it is positive. So our direction, we look at the direction, yes, it is positive, and the strength of the direction is 779.6. Like Godwin explained that a unit increase in the year of service will cause the price, will cause the salary to increase by 779.6. And then when we come to our p-value, we are seeing that it is less than 0.05. So we can confidently say that since our p-value is less than 0.05, because what we are seeing here, it is 0.0000, then you put 12 decimal points and 753, which is even very small. So we are given the probability of committing a type 1 error. It is so small to 0.0005,753. So in this particular case, we what we do, we reject the null. We reject the null hypothesis and conclude that there is a relationship between the years of service and salary. Okay, I think that is clear. You can still move on, and yesterday we looked at the overall p-values and then the multiple R squared and then the adjusted R squared. Okay, now I'm going to move on, then I'll combine the questions at the end. Let's go back. The first example, I was looking at a continuous variable, which was years of service. I want us to look at a scenario in case we are considering a variable that is categorical in nature. I said I'll be glad to share with you this data set in case, the script in case you're interested. And the other thing that maybe I should bring also to your attention is that most of the time, when you look at categorical variables, when it comes to R has got a very resourceful way of doing these things. It creates the dummies automatically inside as it is processing the categorical variables. So in this particular case, you don't need to manipulate and start creating dummy variables for categorical variables. R does it automatically. And in case you want to check, because remember, we are going to explain our results in reference to the reference category of the labels. So here, in case you want, it's just, you can run it, or it is just to show you that R can be able to put the categorical variables into dummies. So I created a simple example, but it's not part of what we are doing. And the function that we use, it is called model.matrix. Okay, what model.matrix does for it, it creates the dummy variables for a categorical variable you have in your data automatically. But you don't need to put it there because it is being done at the back of your mind. I'm only putting this across just to let you know at the back of your mind that maybe in your future work, you don't need to create dummy variables because R does it automatically. I'm only giving one example for rank because it is the variable that I want to consider. And then briefly, I show you how it looks like. So I said, okay, let me use res as my object, or the name that I want to see what happens with the rank when it comes to R. So the moment I run, what you're seeing here, it is rank. And then rank is within the data salaries. I run this particular command, okay? And the moment I run it, I'm like, okay, can I see the first head? We said when you type head, you want to see the first 6 rows because with the rank, I've got 3 categories. One has got assistant professor, associate professor, then professor. So in case I'm creating, if I'm to create dummy variables, then it implies that it is going to give me for only 2 levels. The only 2 levels when it comes to, it's like we are dealing with contrast matrix, what we were discussing yesterday with Professor Susan. So when I enter that, it shows me now that this time around, I've got the rank of, look in the console, it has got the rank of associate professor and then the rank of a professor. Because I'm going to consider, I've already told R that I want to consider as assistant professor as my reference category. This is what I was showing you, that is being done with R automatically. So, but you don't need to include it within your work because the program does it at the back. All right, now let's move on and we run our simple linear regression. But when this time we are considering a categorical variable and I'm considering rank. So I do the same. What is changing here? It's only the rank. I'm calling my model cat2. That is the variable name that I'm giving it. So what I do, I come and run it. Okay, and then I want to see the summary to see my results. All right. Now, when I run R, okay, remember I've considered, I'm still in simple linear, but this time around with a categorical variable. What is happening, like the other outputs that we had earlier, I'm having my formula, which is being given to me from what I stated in R. I'm given the residues, the summary statistics of the residues. We say that it's always better that we minimize the residues or the errors within the model to be as small as possible. So when I move on downwards to the coefficients, look what happens. Most of the time, if you want to master the interpretation of these things, remember we are having rank. The ranks, we are explaining it in relation to the salaries. So in case I'm to consider my output, always the estimate is my reference category. So in this particular case, depending on your reference, I considered assistant professor as my category. So it implies that, so I'll conclude that the average salary among assistant professors is 80776. That is my reference category. Always the reference category is your intercept, okay? And so you can also even look at the p-value when it comes to categorical values, because I'm discussing in relation to the different levels. Now, when you move on to this particular part, line 2, which is the part of associate professor, the estimate you're seeing here, it is interpreted as the average difference in salaries between associate professor and assistant professor. I'm looking at the average difference in salaries between associate professor and assistant professor. Remember, assistant professor is my reference category. So that is the difference, the average difference. So it implies that in case this is my average difference between the associate professor and the assistant professor, then from that point, I'm able to calculate then what is the average salary for associate professor by just taking the additions. Okay, now when I move on to this particular estimate, which is 45996, it is interpreted as the average difference in salary between professor and assistant professor. Everything I'm looking at the difference between what I'm given and my reference category. So that is the 4599. And it's quite interesting is that when we look at our p-values, all our p-values are less than 0.05. So we can we have strong evidence that the salaries of these three categories are different. Let me go to the chat and ask if what I've explained makes sense. Is it okay? Is the explanation fine? Kindly type yes. Okay. Okay, great. Now let's move on. So I'm just giving just one more recap as we're explaining when it comes to a multiple linear regression. What I say that always your reference category is your intercept. So in this particular case, our reference category is assistant professor. And so the average salary of an assistant professor, according to the data that we have, it is 80776. Okay, and when we move on to this particular estimate, the second one, for it, it looks, because we are interpreting the result in reference to assistant professor. The amount 13100, it implies the average difference in salary between an associate professor and an assistant professor. So from that manipulation, because it's a difference, you are able to calculate the average salary of an associate professor because you know what an assistant professor gets already. And then when you come to this particular value, it indicates the average difference between a professor and an assistant professor. So for you to get this, the average salary for a professor is just a matter of manipulation. So in that particular case, because you already have whatever it takes. And given that our p-values are all less than 0.05, we can strongly say that yes, there is strong evidence that there is difference in salaries of the different category of the different ranks that we are given. I'm going to go back in the chat and ask, can I proceed? Can I continue? Type continue if it is okay. All right. Okay. From what I'm seeing in the chat, people are saying that I proceed. That's fine. And then for the last one, I say that you now, in case you want to go on to a multiple linear regression. Remember yesterday I mentioned that sometimes in case you have many variables and you don't want to write one by one, all you need to do is to put a dot, okay? So I'm running now a multiple linear regression that has got both all the whatever variables that I have within my data set, they are being combined. So what I'm going to do, I called it cat variable, I run that, and then also I proceed to get a summary. So from the results that we are having in this particular case, okay, now given that we've combined all the results, all the variables that we are having, the same output that we are like the rest. We have got the residue summaries. We are given now, we are given, they have considered the different ranks. We brought in the discipline. So in this particular case, we're only having discipline B. So it implies that I'm explaining the discipline variable. You're going to explain it in relation to discipline A, because what we are having here, it shows you the average, it shows the average salary that that is earned, the average salary that the average difference in salary that is earned between discipline B and A. So the same interpretation that we had above, it's the same interpretation that you bring on the general model on the output. And the rest of the explanation is the same. What is important? How do you understand, how do you explain the estimates? And then how is the hypothesis, is the null hypothesis, have you rejected the null hypothesis, or you failed to reject the null hypothesis? And with that, we test with the level of significance alpha, which is equal to 0.05. And you either reject or you fail to reject. So that was the exercise I wanted you to do. So I'm going to stop there. And I'll end on linear regression. Now I want to move on to model building, but you're still going to refer to the same thing, because yes, sometimes we create many models, but the point is, among the many models we've have on the different data set that we've created, which one is appropriate to be applied on the data that you have? We cannot say the best, because sometimes you might say that, okay, yes, this is the best model that I have. And then somebody else comes up and challenges you, like, no, I use the same data set, but this is the model that I use. So now, right now, most of the time we conclude that the appropriate model for this particular data set that I have, it is this one, or when you state it. So I'm going to close this and then move on to model building. I'll stop sharing and then share another slide. Okay, there we are. Now, we are moving on to another interesting concept when it comes to regression models. whatever concept that we are learning today can be applied on other models, even on generalized linear models. We talked about just briefly on what they are yesterday. So when it comes to model building, because you've got your data set and you want to understand, okay, among the different models, maybe that can be merged from my data set, which one would be the most appropriate? That is what we call model building. The way you see a house, okay, that as you're going to build a house, you start from the foundation, and then you put, you get the bricks, and then you build the one side of the wall and so on. So this time around, it just have that explanation at the back of your mind, that it's what we are still going to use. We are going to build and see which model is best for the data that I have. And in the end, I'm going to give you an exercise to get for me a suitable model that fits the salary data set. So that is the assignment I'm leaving. So pay close attention, and then you do it later after the session, and you can present to us tomorrow. Okay, so when it comes to model building, remember, we are looking at one thing. We have got a dependent variable, which is being affected by various independent variables. So the point is, what we are going to do, you can add, and then you can also delete different variables, because by the end of the day, not all the dependent variables will influence or affect the independent variable in the same way. So in case you're building up a model, you might find that, okay, for example, we've just looked at the salaries data set. Maybe you can, the moment you add the year of service, and then that is as your variable, it might be significant that it affects what salary. But then as you keep on adding another variable, for example, let's say rank, and you find that it's not significant. So what do you do? What we are going to look at, there are various methods on how we are going to build our models. So the point is, you either add a variable. The moment you add a variable and still the model stays significant, it implies that significant in the sense that it is less than 0.05. It implies that that variable is very good. But in case it violates that criteria, then it implies that that variable is not good for our model. So there are various methods we can use. We can use an F-test. In this particular case, when you're using the F-test, for it looks at the determination of the amount of the reduction in the error sums of squares resulting from adding one or more independent variables to your model. Now, given that I don't want to move on to use the F distribution, I'm going to opt for another option. There are two. You can either use an F-test, or you can use a p-value, and it's what I want to really dive on, but you can use any of them. So the point is, if you don't use an F-test, you can use a p-value criterion, whereby you are able to ask that, okay, in case I add a certain parameter in my model, is it really significant, or is it of greater advantage that in case I miss out this particular variable, then it implies that my model is going to give me a bad fit. So that's what we are going to look at. However, I also want to let you know that there are various packages that you can consider, especially when it comes to model building. For example, like MinTab and then SPSS. It gives you the various options that you consider. But in our case, we are going to do everything into R and see what conclusion can we come up with. And when it comes to model building, like I mentioned earlier, it's like we want to subset, like the word subsetting. You might have, for example, 10 variables, 10 independent variables, and then you want to subset or pull out the variables that you think are the most important. So whatever that we are going to do, it's called variable selection approach, or the variable selection problem. From the slides, the term regressors, the way you're seeing, it refers to the variables because they are the ones that we're going to put in our model. And so the various methods that we are going to use that support variable selection, they are termed as stepwise type procedures. Okay, so within the slide, I see a very simple example. Assuming that you're having your equation, a multiple linear regression model. I considered my Y to be growth. It is just an hypothetical example, but we are going to apply everything on our data set. And I say that maybe growth of a crop is being influenced by rainfall, soil type, variety, sunlight, and then fertilizers. That is the concept that I've picked, okay? So my dependent variables are the ones on the right-hand side, and then my dependent variable is the one of growth. Maybe a growth of a plant is affected with the various dependent variables, but I want to find out among the many variables, which one will be the best. So for the line that you're seeing down here, I just wrote it in a statistical way, the beta naught, which is my intercept, my x1, and so on. Okay, now let's move on to variable selection procedures, or the approach that I want to use. There are three approaches we use when it comes to variable selection. Number one is the stepwise regression. We've got forward selection and we've got backward elimination, okay? And then after having all the three above, what you have to note in mind that they are interactive in nature, and they all involve, like, you add one dependent variable at a time. You ask yourself, okay, does this variable that I'm putting important, or it is not? Then I remove it. So we are adding a variable one at a time. In case it violates my concept of alpha, of when it is not less than 1, then it implies that I'll have to delete that variable that I put, and I remove it. What we are adding and removing are the independent variables, because we want to see how they affect the dependent variable. So we are going to look at forward selection, we look at backward selection or elimination, and then the stepwise. Okay, and then thereafter, we are going to look at the best subset regressions that we've gotten on the three types that I've mentioned above, and check out which one is the best. However, I also want to alert you that there is no guarantee that the best model would be found, but let's move on and see what criteria are we supposed to look at, and then the ones that should be met. Okay, I'm going to start with, like I mentioned already, that there are three methods: the forward selection, the backward selection, and then the stepwise. So I'm going to begin with the forward selection. And then I'll go in the chat and ask if you're following me such that I proceed. When it comes to forward selection, how does it work? Most of the time, the assumption is that you begin with the assumption that there is no regressor. In this particular case, I mean that there is no independent variable. We've seen how we can write an equation whereby it has got only an intercept. Most of the time, instead of writing the dependent variable, we put a 1. Okay, we assume that there is no intercept. For forward, because like you hear the word forward, we are going to put in variables one by one. Now, when you look at it in terms, so in this particular case, it will imply that my Y will be equal to beta naught. If you run it in R, okay, the criterion that you're supposed to check, the result that you get, is it less than 0.5? Okay, the moment it is less than 0.5, then now you start adding a dependent variable that you want. For example, assuming that we ran the beta naught and it was 0, it made the criterion that it's less than 0.05. So we move on, we start adding. Based on the equation that I talked about, the one of growth, there was a variable which was soil type. Then I'm like, okay, now let me add soil type and see if it affects growth. So the moment I add soil type, I have to ensure that the p-value that I get for the soil type, it has to be less than 0.05. The moment it's greater than 0.5, then automatically I'll have to delete that variable. Then I'll say that it does not what? It doesn't add anything on what I have. Okay, and then most of the time you pick a variable that has got a highest correlation with your dependent variable. Okay, now so the procedure still continues like that. I pick another variable. The moment I pick another variable and it is still showing me that, yes, I put the soil type, which was less than 0.5, I keep on adding another one. If it is also less than 0.5, then that is a criteria that I can proceed. So within our slides, whatever that you're seeing where there is F statistics, consider alpha, which is less than 0.05. Okay, now I'm proceeding. All the whatever that I'm talking about, they are within the slides. I can keep on adding other independent variables. For example, from what I looked at, for me to consider that this model was good for, in case of word selection, all my p-values are supposed to be less than 0.05 for each variable, for each independent variable that I include in my model. But you know what, it's very interesting that you're not going to go through all this struggle of checking whether it is less or greater or what. R does it automatically, and it's able to give you that, okay, in case you're considering forward selection, all what you need to do, you tell R the direction. I'm going to show you the different, the command that we are going to use. You just command R that, you know what, just put the direction as forward. And then in the end, it will look through all the variables that you have, and it will give you a final model that is suitable for your data if you're to use forward selection. Let me go in the chat and ask, are we on the same page? Can I proceed? Can I continue? All right. Great. Okay, now let's move on. Now I'm moving on to, that was for forward. The principle is you first consider your regression with only an intercept. Let's move on now to backward selection. Now with backward selection, we are going to move backwards, the way you hear the word backward selection. So this time around, what happens is that you first consider your model with all the variables. With the example that I showed on the second slide, which had growth, it had 6 independent variables. So this time around, what you do, you set a linear regression model, and you consider you include in all your variables, okay? If you remember the dot sign I talked about, that y is a function of dot. The dot implies that you consider all the variables within your data set. And now we start working backwards with the backward selection. What it does, it is going to go and check. It also eliminates one at a time. Remember the procedure. It eliminates one at a time. So what it's going to do, it's first going to look at one variable, which has got an alpha that is greater than 0.05, because in that particular case, we'll be violating the null hypothesis when it's greater than. What we want to do is to reduce the probability of committing an error type 1. So it will start with one independent variable, which has got an alpha greater than 0.05. It will eliminate it. It will remove it. And then the procedure goes on, okay? And it will also continue and keep on eliminating all those variables whose alpha is greater than 0.5. So in other words, for it works backward, yet for forward, it works as moving ahead. With the backward, you put in all your variables, and then R automatically, like I said earlier, you can see through the different steps, or you can ask R that, okay, with the backward selection, get for me the best model. Of course, the best model, like I said, it's the one that has got whereby all the variables are significant, or they are influencing the dependent variable. Okay, now the last one is the stepwise. With the stepwise, for it combines both. It combines the forward and combines also the backward selection procedure. Okay, so in this particular case, it looks at two levels of significance: the one of forward and then the one of backward. But most of the time, it starts with a forward, whereby you start with only an intercept. And the moment alpha is equal to 0.5, it will continue. But the moment you add in another variable, for example, in this particular case, when you can add rainfall, and then rainfall shows you that it is significant at 0.05. So when you proceed and you add another variable, for example, soil type, And then it shows you that rainfall this time around, when you add another variable, it becomes insignificant. What it will do, it will now delete out rainfall and stays with only a variable that will be significant. So for it, it works forth and back. It looks at, you can add in a variable which showed that at forward it was significant. But when you included another variable and the next step, what you added in earlier, it is insignificant. With a stepwise, it will delete it out. And then in the end, it will only give you what is significant. Okay, so the same procedure continues. And then also in the end, it gives you the variables, the independent variables that are significant to your dependent variable. Okay, like I mentioned earlier, that none of the methods result into the best regressors, but all we need to say is that among the models that I've set, okay, the appropriate model that I get, it is A, B, C, and D. Okay, now having looked at the forward, the backward, and then the stepwise method approach. Now, so it implies that those three approaches are going to give you three equations, but you need to pick, I mean, of which is the best. But most of the time, when you look into literature, you will see that the backward and the forward, most of the time, they give similar result, but it still varies from data to data. What works for the other person might not be the same for you. So what happens is that when you run the various equations, most of the time the criteria we're going to consider is you have to ensure that among these many equations, the R adjusted must be the largest. Which of these three equations has the largest R adjusted, R squared adjusted, or the one with the smallest MS, the mean square error? It's considered the best. And also the other criteria that we can consider is the AIC, the archaic information criteria. The one that is the smallest tells us that, okay, that is the best model. We can also look at the MARO-CP, whereby for it gives you it is equal to the number of parameters that you've used in the model. So, for example, in case we considered an equation that has got 4 variables, so it implies that with the 4 variables, each variable has got a parameter, the beta naughts, beta 1, beta 2, beta 3, and then beta 4. However, remember, we also have the intercept. So it implies that that particular equation will have 5 parameters. So what the MARO-CP tells us, that the best model will be the one that gives us, the P should be equal to the number of parameters that are being set in that particular model. You can also look at the prediction sum of squares, and the one that gives us the smallest value, the smaller the press value, the predicted sum of squares, the better the model's predictive ability. All right, so whatever I've explained, I'll put it in more details in the following slides, but that is the criteria, those are the criteria that we are going to base on. And then now, after deciding out that, you know what, having used forward, having used backward or the stepwise, and then you tested the evaluation, you looked at the adjusted R squared, which is the biggest, you looked at the AIC, the one that gives you the smallest value, you considered the CP, which gives you equal number of parameters in the model, and then you also looked at the one that gave you the smallest mean square error. So after seeing that all those evaluations are being done, now you pick the model that you've evaluated and then proceed on to do the analysis like what we've been doing before. Okay, now that is the end. So we are going to move on to R. I'm going to stop sharing and then ask in the chat. Is what I've explained clear such that we move on and do it practically in R, or you have a question? If you, in case you have got some question, please text them in the Q&A. There it becomes very easy for us to see them, because if you put it in the chat before I read the question, more people have sent in more charts and becomes pretty hard for me to retrieve them in a short time. In case you've got questions on what I've explained, kindly put them in the Q&A. There's some other questions. Professor Susan is going to answer them, but I want questions on what I've just explained, and then I answer them clearly. If we don't have questions there, then let's move on to R and see how can we do it practically such that we are able to understand this concept very well. Okay, before I move to R, let me share something very small such that it clearly also helps you to understand what I've been explaining. It's just an example, a few slides, and then we go to R. Yeah, that is the part. I explained that initially, so maybe we'll talk about it later. Let me ask in the chat. Okay. I want to share a simple example on backward selection, but this example is by by Something Southwestern. Are you seeing it? I just want us to walk through it briefly, and then we go to R. Are you able to see my slides with an example? Okay, great. Let's just walk through it. It's very easy. And then later we move to R, such that by the end of the day, I also want you to do the same on your own data. And then I've already told you the exercise I want you to do. You're going to do the same on salaries data set, and you tell me which is the best model when it comes to salaries data set. Now let's proceed. Now we are looking, I'm just giving an example for only backward elimination or backward selection. Remember what we talked earlier, that with backward, it considers all the independent variables at a go, and then it starts eliminating one by one. So let's see it here, such that when we go to R, you can easily transfer the knowledge that we are talking about now to a practical session. Looking at this particular example, the Clarksville homes. So what happens that Tony is a real estate investor, just moved to Clarksville and wants to learn about the city's residential real estate market. Okay, so Tony has randomly selected 25 houses for sale listing from the Sunday newspaper and collected the data partially listed on an upcoming slide. Let's see what happens. So we want to develop using backward elimination procedure, a simple regression model, which will be able to support Tony when he wants to predict the price of selling a particular house. So this is what we are having. This is the data set. Let's consider it as it's just partial data set to just support us understand what exactly happens when it comes to backward selection. So among the variables, we have a segment of a city. Either it is categorical in nature. It's just an example. Remember, the price for selling a house, which is in dollars. And then we've got the house size in square feet. We've got the number of bedrooms in that particular house, the number of bathrooms, and then if the house has got a garage. So what we are seeing, these are the characteristics of the house that Tony wants to sell. The price, the size, the number of bedrooms, the number of bathrooms, and the size of the garage. So let's see, how are we going to create, how are we going to get our best model with backward elimination? Now, what happens is that, like I said, we put all our equations in the regression model. So this is an output. I want to just explain about the regression output that we have, and then later we move on to R. So within our output, column B shows the coefficients. We've got the standard error. We've got the t-test. We've got the p-value. I mean, this is the output that we've been talking about even in the other things. The output we are having in R. This is the same output, only that it is being generally put in the table form. I've got the intercept. You consider the house size, the bedrooms, and then the bathrooms, and then the cars. So looking at the output, what happens at the background when R is working out? It looks at the variables, and then among the variables, it looks at, it first considers the one which has got the greatest p-value. That is when p is greater than 0.05. All right, and looking at our values here, you see that when you look at cars, the p-value is 0.6968. Okay, yes, it is insignificant, but there are also other variables. But what it does with backward elimination, it first eliminates the one with the greatest p-value. So it will remove the cars, and then on the next step as it runs, it will remove the one with another p-value that is greater among whatever it's left. So that is what is happening on this slide, and the explanation is here. So the car variable is removed from the model, and then a multiple linear regression is performed again because it was removed to as greater than 0.5. When you move on, now among the variables that we have, we've remained with the house size, we've remained with the bedrooms, and then the bathrooms. On our p-values, another one that has got a greater p-value, which is greater than 0.05, on the variables, it is the bedroom, which is 0.28113. So what it's going to be done with this particular method, it is now going to eliminate bathroom, because it is now the second greatest with the p-value greater than 0.05. The same explanation. After doing that, then again, a multiple linear regression is performed. Now it's performed again and see the remaining variables. So now when we move further, it still shows you that there's also another variable that is insignificant, which is also removed. Now, what the package does, it removes bathroom, the variable, because it also has a p-value greater than 0.05. Let's see. So when you look at our model, what is remaining with backward elimination? It's only one variable, which is the house size. So now, when we come further, when you run the model again, we're only saying that among the many variables that we have, the backward elimination is telling us that it's only the house size that Tony has to consider when he wants to do what? When he wants to sell the house. So this is the one that has the p-value, which is less than 0.05. So finally, we conclude that house size is the only independent variable which is best to influence the price for the house. And this is the estimated or the appropriate model for the particular data that we have. And then you do the explanation normally. That is the example that I wanted to show you. So I'll end here and then now move to R. Prof, answer that. Okay, now let's move on to R. Huh? Now, we've gotten, there's a question in the chat that what about the intercept? Remember, as we keep on, this intercept is going to keep changing depending on what models are being eliminated, what variables are being eliminated. Because by the end of the day, if I remove one variable, okay, if it is deleted, then it implies that as I rerun the model again or the equation again, that intercept will keep on changing. So now, looking at what I've just shown, in case I eliminate the size of, in case I eliminate the house size, then it implies that I'll only have a price which will be for this particular data, which will not be independent of anything. Okay. So will you mind sending I have no problem. I can send you that, but it was just a quick example just to support you to understand. Okay, let's move on to R and move on. I'm using the follow-up linear reg 2, the one that I sent you yesterday. We are still using the same data set, and we are going to move down to the commands for variable selection. But in this particular case, remember, we need to load our libraries. And I'm going to use the diamond data set, but for your practice, I encourage you to use, as your homework, you use the salaries data set. Okay, let's go to R. Hope you're all there. I'm going to load my libraries. Okay, why shouldn't I do a univariate analysis? The point is that you're having many variables. If you start working out one by one, you're going to take a lot of time. But like I told you, the point is R does everything for you. I was just going through the various steps such that as we go to R, it supports you to understand the output that you are going to get, such that you do not see, I mean, how did we get the results? Okay, so that is the I was doing it that way. But if you want to do it manually, but I mean, we're in the era of using computers, so why should you do it manually? If you start adding one at a go, you'll take a lot of time. And let's look at a scenario whereby you've got like, maybe let's say 20 variables. So what time are you going to take checking to see which one is significant by which one is not significant? Yet there are packages already available that you can use to support you to do a conclusion in just seconds. So Prof, are you answering more questions? Okay. Kindly keep posting the questions in the chat. Professor Susan is answering them out as we proceed. Okay. I'm loading my data set. I'm going to use the one of library. So I don't need the rest. I'm going to scroll down. We've already walked through all those variables. Okay, here we are. We are moving on to working everything in R and see what happens. Variable selection procedures, model building. Okay, remember I'm using my data set diamond. Have it at the back of your mind that your data set might be different from mine, but the procedure is the same. Understand the principles and then apply them on your data set. I'm going to start with backward selection. We said with backward, you put in everything at a go. With forward, what you do, you start with an intercept, okay? And then you keep adding one by one. But R does it automatically, so you don't need to work it out manually. And then with the stepwise, it combines both the backward and then the forward. But let's start and see. So, we are using the same equation, okay? I've got a linear equation, my LM price, a function of dot. Remember what we talked about dot? Everything, all the equation, all the variables, the independent variables are considered. So I call my model fit all. I only put, remember we talked about objects. It depends on what you want to name it. It can change. So I run fit all. This is my equation that I'm considering, backward selection. So I'm going to run it. It's the normal LM that we've been looking at. And then I ask for a summary fit, if you're interested anyway. Okay, the moment I ask for a summary fit, this is what we've been having. It has considered all the independent variables within the diamond data set. Now, sometimes in case I've put many equations just to help you in how you can manipulate these things. So you can, some of you can eliminate them, but provided you can shift these commands and you fit them to your data. That is the most important. Sometimes you might even want to see the formula of the different variables that you've considered. So I click on formula, then fit my model. Fit all is the model, the backward selection model that I'm going to consider. And I say all. So when you come, when you look in your console, you are able to see that when you look in your console, you're able to see the formula that you are using, your linear equation, that price is a function of weight, quality, color, length, width, and then depth. It is considering all the variables. That is our model, okay? Now, or you can type formula and then fit the same thing. I'm not going to run that because it will give me the same procedure. Now, the command that we use is called step, okay? We are going to use the step command. And inside the step command, remember, like we've always advised you, that use the help command in case you feel that something is not clear. Ask with the help command such that R attaches more info for you and you get to understand how exactly you're supposed to use a particular command. So what happens within the step, okay? Inside there are different arguments. For example, the object, that is number. Remember the object, what we talked about, it's what you've named your equation. In my case, I've named it fit all, okay? The scope, it will tell you, I mean, among the many variables that you have, to what length do you want to go? Maybe I type whatever I'm talking about, such that, okay? Let's type help step, okay? And then let's click run. When you click run and you come, when you click run, look in the help window and see the more details that have come there, because the help is an inbuilt function that's supposed us to understand the different commands very well. All right, now when I type help, it shows me that a step, the arguments that I've got, there is object, that is the linear model that I want. It has given me the scope that, so it tells me to how far do I need to go among the different variables that I've got. Then the scale equal to 0. This is by default, okay? Sometimes you might not want to see the various steps that are involved and you're commanding R and you're telling it that, you know what, just give me the final model. Don't show me the steps that you've used. And then we've also got another argument called direction. So within the direction equal to C into. So here you can decide, in case you want to use a stepwise, you put both, or it's a backward, or you can pick a forward, okay? And then it has got the trace, then you keep null and so on. For more details, these arguments are being explained, what they tell you, the scope, define the range of models, examine how far you can go. The moment you put a scale, it will tell you what is the AIC, the archaic information criteria that you need to consider. Then you can also talk about the direction, the trace, etc., etc. I think now that is okay. Now let's move on to the step. So what I did, I considered my step, I fit in my model. Sorry. Okay. All right, hope it's clear now. Is it clear now? Okay. Okay, let's move on. I'm using now the step command. We've just looked at the help command, what is entailed. We start with the object, and my object is the equation, is my backward, it's my regression model that I'm going to consider, which if you see in the console, it's already there. So I fit all my object. The direction that I want, it's backward. Okay, so I click on that, and then I run. So the moment I run, I need to go and check what is happening to the variables that I have. Kindly pay close attention. Using the backward selection, we said that what it does, it eliminates one variable at a time. Actually, the principle applies to all the selection procedures that we are having. So it is telling us the first AIC. Remember, AIC is important because it's one of the criteria that is going to help us as we're evaluating these models to come up with a conclusion that among these three, this is what I'm going to consider for my data set. Okay, it is telling us that AIC is 1464.8 at the start. Okay, and when you move down on what it's saying here, hope you're seeing a minus sign. Remember, with the backward selection, it keeps subtracting. It is telling you, it is giving you the DF, the sums of square, the residue sum of squares, and then the AIC. That from this particular, from my regression model, the one that I'm having here, sorry, what I want to highlight this. Okay, when you look at what I've highlighted, now R is telling me, because that is the overall regression model that I have from my data. It is telling me that at the beginning, my AIC is 1465.18. However, if I remove depth, we remove one at a go, okay? In case I remove depth, my AIC will reduce to 1463.4. So what it's going to do, the next step, it is going to remove depth such that my AIC reduces to 1463. Remember, the smaller the AIC, the better. So we picked the smallest. Okay, that was step one. So with this, I've not put any conditions, but we are going to see another condition in case you don't want to see these steps, what happens. So when you scroll down, okay, maybe let me first, when we move on to step two, what it's going to do, it's going to remove width, because it is also telling you that the moment you remove width, further, your AIC will reduce again to 1643, because it reruns the equation again. As you remove one model, it reruns again. But one thing I want you to note at the back of your mind, the most important step is this particular line here, which has got none. The moment this model is going to run backwards until we'll see none on top. None is it is like the stopping point. The moment we reach to none, it is telling you that there are no other variables that can make your model better. So stop here. Okay, so let's proceed. I'm moving on to the next step. The next step, we are going to see that it has removed depth. Okay, now look at my line here. I don't see depth anymore because it has been removed. Now it is telling you that please go ahead and remove width. It is giving you a step by step, and it's telling you that the moment you remove width, your AIC will reduce from 1463.36 to 1462.0. So it implies that in the next model, our current AIC is going to be this one, and the model is going to rerun when removing width. Okay, I proceed downwards. Now it is telling me that step 3, these are the steps that I showed you on the slide. It is the reason why I wanted you to look at them such that it's clear here. When you come to step 3, it is still further telling you that, you know what, now this is the equation that I have, but it's telling you that yes, remove length because it is also not significant. The moment you remove it, it implies that my AIC will reduce from this now to this. I've put it in the chat. The AIC, it's the archaic information criteria, the one that is going to help us to understand one of the criteria that we're going to base on to tell whether the model we've chosen is good or not. And the condition is the archaic information criteria that gives you the smallest among the three models that we're going to have. The one that will give us the smallest, it's the one that we'll consider, and we say that the model that we have is appropriate for our data. So that's why it keeps on iterating and it moves on. So it keeps on reducing up to when we are going to reach a time, and it will tell you that in case you add in more, you're going to increase it and you're going to create a worse model. Okay, now on the next step, we want to remove length, okay, from this model here, from what we are having. So I want to remove length, and it's telling me that my AIC, the archaic information criteria, that when we hear the word information, we want it's something that is going to support us when we are evaluating whether the model is appropriate or not. So that what? I haven't yet reached on the selection procedure. Kindly be patient. I've not reached on the selection procedure because we are. Okay, fine. Kindly be patient and we proceed. Then we are going to combine because the final model for every procedure, for every variable selection procedure, we are going to check. We will be excuse me. We'll be comparing the AICs of the three models and check which one gives us the smallest. That is the instance of the AIC. Okay, let's proceed. Now, what we are going to do, we are going to remove length. Okay, when we proceed down, now it is telling me that my AIC, the archaic information criteria, it's 1460.64. But when I look down here, I've reached where it is telling me that none, that in case this is, it is like the stopping point, don't proceed. It implies that the remaining variables that you're seeing in the model are the ones that will give you the best, the ones that will give you the best output in case you're doing analysis. So we are going to stop here. And then if we go ahead and bring in whatever that is below, because when you look at the AIC here on this particular side, they keep on increasing. So we are going to stop at this AIC, the 1460.64. So that is with the backward selection. The none is the stopping point. We cannot proceed anymore. So what you note at the back of your mind is that the model that you're seeing here, it is the one that R has selected for you as the best model, as the appropriate model for the backward selection with three variables: weight, quality, and color. It is the same as the other example that I last explained on the slides. Okay, I'm going to go back such that we move on. Also, residual sum of squares. RSS is the residual sum of squares. Remember that whatever that we are doing, it is still in linear regression. So don't forget the concept, the residual sum of squares, the mean square errors, because we just need to attach from the knowledge, the statistical knowledge that we have. It's one that we want to apply on our data to see that we get the model that fits, that is appropriate on our data. Okay, so those are the results that I was explaining. I stopped at none because with the backward selection, it has given me that. I can't proceed anymore. And now, when I come to this line, I didn't do anything. It's something that I did. What I did is that I just created an object, back_AIC. This is what I changed only. but whatever is on this side, it is the same. I just wanted to create an object. I'm going to come and run this line. Okay, now in case I want to see the previous information, I just need to run my object. But now I'm not going to do it because I've already explained that. And the moment you run it, still you see, it will give you the same output that you have. Okay, that what? I can't. Can I proceed? Are we on the same page? Kindly type proceed in the chat. Anyone? No. In the morning, I sent them all the links, the recorded links. Yeah. Okay. In the chat, I'm saying proceed. Kindly repeat the AIC. We've got the recorders. Do some. All right. Let's proceed. Let's proceed. But I hope by the end of the day, before we end our session, because we've got an assignment that I want you to do, and please make sure that tomorrow we get the first 3 people to present to see whether you've gotten this concept very well. Now, from remember the evaluation, for me to do an evaluation, there are some things I need to test to see which the ones I'm going to compare with the forward and then the stepwise. So for me to check the Maro CP, which is gives me the number of parameters in a particular model, and then the AIC, like now I'm getting the final summary of everything. So I use the command extract AIC, that extract for me the archaic information criteria. So what this command does, it considers the best fit, okay, the appropriate model, the final model that it has chosen, and then it returns for me the AIC, and then also the p-value, the p, sorry, not the p-value, the Maro CP, okay? So when I run that, it will tell me that that particular equation has got 12 parameters, and then the AIC, the archaic information criteria for the best fit is 1460.641. All right, and then I can also print the coefficients in case I'm interested to understand how my coefficients behave. The coefficients within that model. Maybe you can ask yourself, but how come we've got many parameters? Remember, among the variables that we have, we've got those that are categorical in nature. That's why you're seeing that we are having many parameters. For example, the color, and then the quality, it has got 4 levels, and then the color has got, I think, 6 levels. That's why we are having many of them. And then also, I also want to get the adjusted R squared, because I said the R squared that will be biggest for all the 3 models, it's the one that I will choose to support me to choose the appropriate one. So I go and say, I want a summary of my model, this one here, okay? The one that is the one for the backward selection. But remember, I labeled it as back AIC as an object. So, and then I say from it, give me the adjusted R squared. So I run that. The moment I run it, is telling me that my adjusted R squared, it is 0.88. Okay, and then also, I want to get the mean square error. Remember, with the mean square error, we said that the one that gives you the smallest MSE will be the one that it will be considered to give you the appropriate model that fits your data. Okay, so now the formula is here. So I get the mean within the mean square error. We are calculating the mean square error for the back underscore AIC model, the one that fits well with the backward selection. Then in it, I take the residues to the power 2. This is the formula that we're going to use. So mean of everything within our model, and then get for me the residues, because the point is, remember, we need to reduce the error. Our errors should be reduced to a very minimal level. So when I run this command, I say, and then I want to see the output. So it is telling me that my MSE for the backward selection, the back AIC, it's 1734819. So that is for the case of backward selection. Remember, we need the last summary outputs, because we are going to compare them with forward and then stepwise. And then from them, we suggest that, okay, maybe as far as my data is concerned, I'll consider a backward. Okay, as far as my data is concerned, I think the forward is the best, or the stepwise fits better than the rest. Let me ask in the chat, are we on the same page? Okay. Professor Susan has sent the links in the chat for the different recorded videos. Yes, they're already on your emails, but in case there's some people who missed them, kindly pick them there. Does it mean that backward and stepwise will give different results of AIC? Yes, yes, the answer is yes, but it all starts from the data. Sometimes the AIC will be different for all the 3 models. Sometimes, yes, they can be the same, but at least you have to see whether the evaluation criteria have been achieved. So we are going to do the same thing. We need to find the AIC. We've got for the one for the backward, we've got the adjusted R-squared for the backward, and we've also got the MSC for the backward. We're going to do the same thing for forward. We do the same thing for stepwise. However, it's quite interesting, like we said, these models, not all of them, but they guarantee you that the output that you've gotten is the best. That's why I told you at the start that you say it is an appropriate model. Okay. Yes. We conclude that it is an appropriate model that supports you to clearly analyze your data very well. All right. Please paste command in the chat. We don't have it really. Okay. Let me paste it. So I've pasted the command. Now let's move on. That was for the case of backward selection, backward elimination, or call it selection. But the point is now the principle is you start with all the variables and then you start eliminating one by one. Let's move on to forward. Okay. Remember the formula we're using when we're calculating the mean square error, whereby the point is that we need to minimize our residuals. We said yesterday that a residual is the difference between the observed value minus the fitted value or the predicted value. So those are the residuals. And the moment we keep squaring them, then it implies that you're trying to reduce the the errors, how far the errors are from the fitted line. Okay, let's proceed now with the forward selection. When you check in the script that I sent you, like I mentioned yesterday, all those green comments, they are to support you understand what is being done. So take time and read them. Okay, now I move on to forward selection. Remember what we said, that with forward selection, okay, you start with an intercept and then you keep on adding one variable at a time. However, with R, for it, you just need to command it and then it will do what you want. Okay, so this is my equation, my linear regression, my linear model. So my intercept, remember when you're writing out an intercept, the beta naught, it's 1. Okay, so price is a function of 1, which is my intercept. So in R, that's how we define it. And I've created an object to name my model as fit start. Okay, from there, I run it, the usual way we've been doing it. And then I can also see the summary, what happens from my data. The same explanation applies. I'm not going to explain this again because we need to move on. This is an equation for an intercept only, and we are given that our intercept is significant. So let's start adding in more equations. So what happens in this particular case is that the moment you put in, now I move on to the step command. Remember, I'm supposed to use the step command. We've already checked in the help to get more to understand what happens in the help command. And by default, most of the time, the scale is equal to 0, okay? But it's asking you, in case we want to include in another argument of scope. The scope tells us how far we can go. But let's first see, in case I run this particular line here, which has got fit start, the fit start is my regression model, which is now the intercept only. It has only got the intercept only. And then the direction, I'm saying forward, okay? The moment I click there, when I check in my R console, it is telling me the AIC is 1665.81, okay? And the equation, that price is a function of an intercept, which is 1. And it is giving me the intercept. Remember, I'm moving forward, but only this particular information that I have, it doesn't make sense for now. So what I do, I go into R, and now I look at the scope. I bring in the scope argument, okay? I bring in the scope argument. Within the scope argument, remember, it is telling me that, okay, I've started with an intercept and I want to add in more variables, all right? Maybe I add in length, maybe I add in color, but what I want to do is that for me not to waste time, I'm going to tell R that yes, it is a forward direction, but the scope I want you to look at, consider all my variables. That's why I'm having this argument that scope is equal to formula fit all. If you remember, we looked at this one previously, that you know what, consider all my variables, and as you keep adding one at a go, remove the one that is not significant, okay, to be appropriate for my model. All right, now that is, so from here, I've only added this argument for scope. So I run it. The moment I run, then I want to see my output. I can do the same thing. The moment I run, kindly work with me through as we are. So I'm going to go from the start again, and let's see the difference. So this is the output that is giving me. With the backward, when you look here, where I'm moving my cursor, if you're seeing it here, we had a minus sign because for it was reducing. But this time around, I'm having a plus. Look at on the output that I have, I've got plus weight, plus width, plus length, plus depth, and so on. Yet initially it was minusing for the case of backward. Now, the explanation is almost the same, but this time around we are looking at forward. So it is adding. Then we're going to move on to another scenario and see, what if you don't want to see all these things and you just want to have a final output? Okay, now it is telling me that for the case of forward, the first AIC is 166.5.81. And it's telling me that in case I add weight, okay, my AIC is going to reduce to 1474.8. Remember, we said the archaic information criteria, the smaller one, the smaller the archaic information criteria, the better that the model that we are going to fit our data is good. All right. Now, like in this procedure, we've not eliminated the steps. So we are going to go through the steps until we get to when it is saying none, that please don't add any more. Okay. Now, when we proceed on step number 2, remember, this is our terminating point. So when I proceed to step number 2, in this particular case, we are adding weight. It's telling us that from here, this is our first equation. Hope you're seeing what I've highlighted. That is our first equation. It is telling that the R is telling us that add weight. The moment you add weight, your AIC is going to reduce to 1474. It's going to reduce to this. Okay, so I continue. Now, when I move to step number 2, now look at my model. It has changed. Now price is a function of weight, and my AIC has reduced to 1475.75. Okay, now when I look again downwards, it is telling me that add quality. The moment you add quality, my AIC is further going to reduce to this, to 164 to 1465.9. All right. Now I'm going to remember we said now it adds one variable at a time. In case you want to see the steps at the back of your mind, you should know that in all the different procedures. So when I continue downwards on the next step, that now I get this is the same the new equation I'm getting, that the moment I add quality, the moment I added quality, my AIC is reduced to 1465.88. And now finally it is telling me that, you know what, go ahead and add color. If you add color, your archaic information criteria is further going to reduce, because we need an archaic information criteria that is small, or which is the smallest among the 3 models that we will have. And we will have that, the AIC. So, but now if I continue further, it is telling me that please stop, don't add any more. So in that particular case, we don't need to consider whatever that is down. That is the chopping point. So now it is finally giving me the moment I see none, then it implies that I'm going to end. So with the forward selection again, our final model it is giving us, it is this one. It is price as a function of weight, as a function of quality and color, with my AIC as 1460.64. It's quite interesting, like I mentioned earlier, all these values, they vary from data to data. But with this data that we are using for price, remember, for the case of diamond, remember, it is just a partial data that we are trying to use to help us understand what exactly we are supposed to do on our personal data sets. So finally, it is the program is telling me that this is going to be the final model you're going to consider. It gives me the coefficients for each. okay? That the weight, the quality very good, and so on. It even gives me the final equation that I'm going to consider. I know you might be asking yourself, but how come maybe the forward, it also gives me what happened with the backward. Yes, it happens because remember what we said, we want to pick a model that is appropriate. So in case the result for the forward as the backward are similar to the one of forward, so that shouldn't scare you. And like, okay, let me move on and see, will I have maybe different results with the backward? But still there are possibilities whereby in case you consider all the different approaches, you're going to come up with similar results, but it varies from the data that you have. Let me ask in the chat, are we on the same page? AIC adding or reducing? AIC is supposed to keep reducing, not adding. We need to get the one that gives us the smallest value, okay? So as you keep on performing the different analysis in your work, as you try to compare various models, maybe you're going to do a comparison of various models depending on the survey data that you have. And then how are you going to conclude that maybe model 1 performs better than model 2 and performs better than model 3? So one of the things that you can look at is the archive information criteria to support you, to show you that, okay, maybe model 1, it has got a higher AIC and model 2. So among the 3 models, the one that will give you the smallest will be the one that you will consider to give you to give you a best fit, to give you a model that will clearly fit your data. Yes, Margaret. Does it mean that you have to do all the approaches to select an appropriate model? The answer is yes. And then you check the evaluations and you conclude. Can the results we get for forward and be different? Yes, it is. The answer is yes. They can be different, they can be the same. Where did fit all come from? Judith, fit all came from the backward. Fit all was where I am having all my variables fit in a regression model. That's why I called it fit all, but the name can change. Okay, can I proceed? Please type yes or no. Was like a vector that. Okay, proceed. Wonderful. Let's pay close attention. Good enough, you already have an exercise. So whatever that I'm going through, you're going to apply it on your salary data set, and then you present to us tomorrow, such that we get to understand whether you pick the concept very well or not. And then you come out to tell us that, you know what, among the 3 models, this one is the one that is that will fit the salary data appropriately very well. Will you have some time on categorical variable? Now, James, you're asking something totally different. If it is different, how can we select the best variable from the data, from your data? You are not going to select the best variable. You personally, you're not going to select the best variable from your data. Now, when you look, okay, let me answer. Now, when you look at these final models, okay, for example, when you look at what I'm showing you here, R has already told you that in the final model, okay, when you're considering forward, consider only weight, quality, and color, period. They are the ones that are going to influence price. The rest of other variables, eliminate them. How do we deal with collinearity among the predictors? Now, in this particular case, after selecting the appropriate model, okay, now that's when you're going to go ahead and check with this particular model that I'm given, that which is the best for my data. Now you go ahead and start testing for the different assumptions. All right. Okay, let's proceed. So what we do, when you look in this line, I did the same thing again, and I created forward AIC as my object. Hope you're seeing this line here. The one that I'm highlighting, it stops there. So sometimes, you know, I've included in another argument. It is the same, but I've added another argument, which is trace equal to 0. Sometimes you might not be interested in seeing all these steps that, okay, it removed the width, then it ran the regression again, removed the length, it ran the regression again, removed another variable. This time around, the moment you command R and you say trace is equal to 0, you're telling it, you're commanding R that don't show me all the various steps, just show me the final model that has got the variables that I need to consider when I'm analyzing. The variables that you'll get, they're the ones that we consider to be the most appropriate variables or independent variables that you're going to consider when you're looking at your dependent variable. So let's run and see. In case we put trace equal to 0, it is only going to give you the final output, not showing you the various steps that we saw earlier. I only involved in the steps just to show you what I was explaining in the slides. So I highlight that and then I run. Okay, the moment I run, you see in my notes that I've put that you're telling R not to display the various steps. If you want to see the results that we said earlier, you can now type forward. You can type forward that, because that is the object that I use, and then you run that. If you run, it will give you the final model. That this is for the case of forward. In case you want to look at the price of a diamond, your business dealer, you're working in diamond, and really want to understand among the many variables that I have. So with the forward selection, it is still telling you, no, only consider weight, only consider quality, only consider color, and leave the rest, because for those ones, they will not influence the price label. We do the same. We do the same like what we did for the backward. You extract the AIC. For the case of forward, you can get the coefficients, you can get the adjusted R squared using this particular, this one here, and then you can also run the mean square error. So in case I want to extract this one, I'll get the AIC and the P. I run my coefficients, I run the adjusted R squared, and then also my MSE. So we are going to do the same approach when it comes to both. This time around, what we are going to do, we are going to change the direction. Instead of writing forward or both, what we are going to do, we are going to put both. And saying that in case R puts in a variable when it is less than 0.5 at start of forward, and then when it adds in another variable and see that one of them violates the criteria of our level of significance being greater than 0.05, it eliminates it and then proceeds. Let me get to the chat and ask. And please share us the final script, okay? From your results, we have there, can you predict? Somebody's asking about how you can predict in linear regression. That is also something interesting in the, could you please predict using the results we have there and interpret? Okay. Yes, with the results that we are having, like I said earlier, it is the same explanation. What the main goal for this one, it is just to support us get the right, this is the equation that we are given, okay? So in case you're having this, you can still run it as an LM and you explain your data the way we've been doing before. So there is nothing different. Now, lastly, because of time, I want to go ahead and look at the last one, which is the stepwise. And what it does, it is the same thing, but only that here, what I'm changing is both, okay? The direction I'm putting is both. And so I can run the same thing. I'm starting, but with the stepwise selection, we need to start with, you start with an intercept only equation. Remember, with the intercept only, we had our price as a function of 1. That's why I'm considering it as my object. So it keeps adding to see if the object, if the independent variable that I've added is okay, then it will pass it. If it adds another one and then the alpha is greater than 0.5, it will delete what I've put earlier and then continues on like that. So it works forth and back, forth and back. That is the stepwise. So I come here and then I say that, okay, now right now what I'm going to do, I create an object for my both direction. So I can run that. The moment you run, you're going to get results. It is still the same explanation that we are having. We want to pick the best model. But now in this particular case, what you're seeing is that it started what I talked about earlier, the start fit. It starts with an intercept only equation. And then when you look here, it tells you that if you reduce your the AIC, if you add weight, the AIC is going to reduce to 1474.8. This is what I'm going to have. All right. And now I continue. So when I add weight, then it implies that my AIC, it's 1474.5. So it tells me as I continue, okay, it tells me as I continue, the moment I add weight, sorry, I add quality, my AIC is going to reduce from this to this one here. It gives you the AIC for each particular variable. Now it tells me, now, so I move on to the next step. I add quality, and still, my AIC reduces from 1465.88 to 1460.6. Remember that none is our termination point. When we have none, it will be our termination point. One thing that I have to show you, to have at the back of your mind, is that when it comes to both, you see that now this particular side, we've got both signs, the plus and then the minus. Where I'm moving my cursor here, it shows the plus and then the minus. Yet for the forward, it was only plus, for the backward, it was minus. But in this particular case, we've got both plus and then the minus. Again, for the none, I cannot proceed because that is the termination point. And it also shows me that this is the what? This is my final, the final model that I use for the case of forward. So which is quite interesting is that as far as my data is concerned, the data for price is concerned, I went through and all the models, the different models that I get for both forward and backward, they are the same. So for the forward, I've got a same equation. For the backward, I've got the same. And also for the stepwise, I've got the same. So in this particular case, I can conclude and say, okay, given that I've got similar result, all I need is that to just pick only one of the one equation, since I've gotten now the right factor, the right independent variables that really suit, that really influence my dependent variable, which is price, and I continue with that. Let me pause in the chat and ask, can the same criteria be used in GLM? Yes, it can. Still, you can do it for logistic regression, you can do it for ordinal regressions, and they support you to tell among the many that, okay, basing on your data, okay, when you run these particular approaches, this will give you the best model. Okay, maybe let me run a conclusion on that. I did the same thing. You run the AIC for both. I ran it. I want to, object. Okay, I forgot to run the previous line. That's why it is giving me an error. The same procedures, it is giving me the various procedures. I extract the AIC for the best fit. It tells me that my coefficients for the ones that I've chosen, the adjusted R squared, which is still 0.883, and then the mean square error. So in summary, what happens, what you do, you create a table. Within this particular table, in your first column, you put the three models, model 1 for forward, model 2 for in the second one, you put model 2, model 3. Then in your columns, you put adjusted R squared. Another column, you put the mean square error. Another column, you put the P, the Maro CP. Then the other column, you put you put yes, I've talked about the adjusted, and then you feed in all the different values. For model 1, what was the mean square error? What was the adjusted R squared? What was the Maro CP in that particular model? You go to the second model and so on. Then you start comparing. The point is that you have to, I've not created that slide. What you have to note at the back of your mind is that the one that gives you the smallest AIC, it has to give you the smallest MSC, that is the mean square error. And then the Maro CP, it gives you the parameters should be equal to the equation that you've considered. And also, yeah, the moment the adjusted R squared should be large. So you conclude that among these models, I'm going to pick this one, which is appropriate for the data that I have. Okay, let me pause in the chat and ask. A request for a recap, please. Is there some assumptions in using these model buildings? Yes, there are assumptions, what we've been talking about. I mean, how do you derive the backward? How do you derive the forward? And then how does the forward come out? How do you put the forward, for the case of stepwise selection, whereby you're using both. So whatever that I'm talking about, those are the assumptions that you have to put at the back of your mind. And then after getting finally, as a conclusion, yes, that is what I was talking. When you want to conclude on the best model, when you look with, if you want to conclude on the best model, like I mentioned earlier, when you check in our slides, when you check in our slides, among the things that you need to consider as you are concluding, I said that, okay, like I've told you to construct a table, you check, you request for the small, you type in the MSE, the mean square error, because the three models give you different mean square errors. You check of which gives you the smallest, okay? Then you also ask for the largest R squared adjusted, or R squared adjusted of the three models, which gives you the largest, okay? And then the AIC of the three models, which gives you the smallest value. The Maro CP, which one gives you, you check whether the parameters that have been considered, the value you've gotten, the value of P, is equal to the number of parameters that are being used in the model. When you run for example, in case you use MinTab or eViews, you'll see that they also give you the prediction sum of squares. And I say that the smaller the press value, the predicted sum of squares, the better the model's predictive ability. And so that's when you'll be able to decide, other than just getting your data and then all the time, for example, the supervisor might tell you, but you know, how come, why didn't you consider maybe, the supervisor might ask you, why don't you maybe consider, for example, maybe you considered certain variables and you removed and you put the rest out, and the supervisor can ask you, why didn't you include the other variable in your model? Or because the moment I see when I to consider, the other variable might also have been important, but you left it out. Most of the time that happens because you didn't do model building to check that among all my variables of the 10, of the 20, that only the 8 variables that I've picked are the one that influence my dependent variable. So that's why it is important that you do model building. Now I'm giving homework. So homework, you're going to use the salaries data set. Do model building, run for me the forward, do the forward selection, do the backward, then do both. And tomorrow, you're going to tell us among the 3 models that you've developed, which one is the best model for that data set. Is that fine? Okay. Is there any condition? The conditions for preferences, they're the ones that I've talked about, the evaluation conditions to consider, to say that maybe model A or B, among the 3, this is the one that fits my data very well or the most appropriate. Kindly do the assignment and present to us tomorrow. I want to see if you've picked that concept very well. So the moment you get the best model, the rest of the analysis remains the same. You can do log transformation in case you see that there is some little bit of noise and so on. Okay. Now it will really help me to handle homework. Okay. I've already sent this data set. You already have it, and I also sent the thoroughly data set on your emails. Maybe I can share it again in the chat. But I wanted to, in the remaining minutes, I wanted us to look at how to analyze categorical data. Well, I don't know whether that is okay with you, or I give you a break of 4 minutes. Then we tackle that concept and we see that it's done, such that tomorrow, then we see how we need to cover, because all this information, you need it to support you in analyzing your data. Okay, let's take a break of 5 minutes. So right now, they are just 12 minutes past 1 in Uganda. I don't know what time is it your end. So I'm giving you a break of 4 to 5 minutes to stretch a little bit, and then we proceed. Okay, welcome back. Is everyone on board? Can we get started? Hope you've refreshed. We have a few minutes remaining, so let's maximize them. And we pick this particular concept. Is also that one. More content will be covered tomorrow, or if time allows, I'll look at logistic regression tomorrow, and then Professor Susan will come in to cover the maneuver, whatever that you want, and so on. Okay, let's proceed. Analysis of categorical data. You can hear me? Can I continue? Okay, great. I'm just going to do this in 5 minutes, so kindly pay close attention, because it's also something interesting when you're doing data analysis, especially when it comes to the bivariate and you're looking at association between two variables. Now, in this case, when it comes to analysis of categorical data, the way you hear the word categorical, so we are only going to look at categorical variables. I sent the notes already, the PowerPoints, but in case there are some people that do not have the PowerPoints, then on the updated emailing list, we'll send them. So under the analysis of categorical data, we are going to see how do we use a chi-square test to test for independency, okay? Because most of the time, yes, for a case of the continuous variables, we saw that we can use a scatter plot, okay? As you're plotting, and then you get to see. Now, for the case of a chi-square test, we use this to test the independence between two categorical variables. Note what I've said, between two categorical. In case you've got two categorical variables and you want to see whether they are related or to test for their independency, we use what we call a chi-square test. Maybe so you can use, they can have 2 or more levels, all right? So in this case, we tend to compare proportions to see whether, there is a difference in the proportion of the different groups we have or not. And so somebody, as we move on, we are going to ask ourselves, because we are going to talk about what is observed proportion, the frequency, and then the expected proportions. But it's quite interesting is that let's know the math behind, and then we do apply it in R. If you've come across what we call contingency tables or cross tabulation, it uses the chi-square principles or the concept in the chi-square. So we look at our data in form of frequencies. For example, when you look in our data, we've come across a command called table, whereby with the table, it gives us the frequency. But now in this particular case, when it comes to when we're constructing our table, we are going to consider only the variables we are going to put inside the table. We are going to put 2 variables. Initially, we are only considering, for example, maybe color, and you say table, diamond color, and it gives you only the frequency for the color. But this time around, we are doing cross tabulation. We are having 2 categorical variables, and we want to see the frequency of color and then the price cut. Within, if you remember very well, we manipulated the price variable, and we created another variable called price cut, where we had the diamonds that were highly priced and the diamonds that were lowly priced. Okay, and now what happens in case we go to R? We are going to put table, diamond color, and then a diamond price cut. So this is the results that we are going to get. And what here we are seeing that among the diamonds of high price, 15 of them are black. On our diamonds that are lowerly priced, 21 of them are black. So we can see some probabilities. We are seeing counts that look on the diamonds. Among the highly priced diamonds, 16 of them are black, 6 of them are gold, and so on. Okay. Now, for us to test the association between these 2, we are going to do what we call chi-square test. So as you're creating the cross tabulations, because we are looking at our table, the table we are having here, we are looking at them as counts. We call these cells. For example, if you're looking them as a table, we can say that this is cell 1, whereby it is showing me that my column, it's for the diamonds that are highly priced and they are black, they are 15. I go to the one of low in this particular column, and then the ones are black. So that's why we call them counts. And these counts are got from the data. However, the counts that we are seeing here, they are called observed counts because we pick them from the data, but we need to compare them with the expected counts. And the expected counts come in when, if you're looking in the case that if the null hypothesis is true. Okay, I've talked about the expected frequencies in contingency tables, and then we're going to use our test statistic. This is the chi-square test. Okay, mathematically, or in most of the statistics textbooks that you see, you come across this particular test statistics of a chi-square, whereby it's looking at the observed values, ij, looking at the column and the rows, you minus the expected, square everything, divided by the total, and then you can read from the tables, but this particular time around, we are going to consider R. It's going to compute us for us everything. So the point is, why chi-square? We want to see how these variables are related. Okay, I'm not going to go into the details here. You can read, they're just questions. We are testing the association. We want to check whether these variables are associated. For example, is there an association between color and price? That maybe a certain color due to a certain color, the kind of price will either be high or will be low. Okay, I'm going to go into R and then add more explanations on this because of time, but you have more in the notes that you can read from. Okay, I'm going to stop sharing this, and then I share the R code, and we start from there. That one? Okay. So can I see in the chat, can I continue with the R code and we see how we do it in the remaining 4 minutes? All right, kindly pay close attention. Okay, yeah. Just a slight communication. We're not going to have a support link today, but during that time, work out the assignment. I'm adding you another assignment. You're going to perform chi-square tests in the salary data set, and you also present tomorrow. So you have 2 assignments to present, the one for model building and then the one for running chi-square tests among the categorical variables in the salaries data set. If you haven't gotten the salaries data set, kindly, Prof, you can share it in the chat. Professor Susan is going to share it in the chat, pick it, and then do that exercise that you present tomorrow in the first 30 minutes. Okay, let me run briefly the chi-square test. First, remember, you need to run, let's run our libraries. You already have this script with you, categorical data script. I already sent it. I load my my working directory, depending on where you are. I load my data diamond head in case I want to see how it looks like. Okay. Now, what I do, remember in the diamond data set, I did some data manipulation because I wanted my price to be categorical. Okay. So I explained this in the previous sessions, how I did it, but I just want to put it to be part of my my variables. Okay. Then I run my structure of the diamond data set. I'm running through because now I know you've picked, you know what I'm doing right now, depending on the command. Deploy, there is no package there. Okay, make sure you run the deployer package. The package that we've been running, we'll keep building on them. Then I run that as a factor. You know, when you put as a factor, you're telling R that, you know what, you're telling R that they are categories. So this is what I'm going to do. I start by making a table for my variables. I know that now color is categorical and even price cut is categorical, but I put them in my object, my table. So, and the command is table. I run this. For me to see the output, I run the table. This is what I was explaining. This side I've got the colors, and then this side I've got the price. They are both categorical in nature. Okay, I want to see if there is an association between the different categories of color with price. You can run the prop table if you want to see the proportions for each, but we already done that. But the most important, before we are closed, this is the equation. The chi-square test. This is what you run. The chi-square test, and then with the moment you run it, what it does, let me run it again. What has it given me? Okay, what I'm having, that the moment I run color and then the diamond price, okay, it is showing me that the chi-square is this. My test statistic is that, my degree of freedom is 6, and then my p-value, though it seems significant, but there is a warning. So as you work out, you can encounter this particular warning whereby it is saying that the results appear incorrect, okay? That the chi-squared approximation may be incorrect. The moment you see that red as you're doing your analysis, two things should come at the back of your mind that you have to correct. There are two solutions you can do. It implies that it means that the smallest expected frequency is lower than 5 in one of the cells. So the solution, one, you can go and merge some of the cells such that you increase the different observations in the observed frequency. But the quickest one for you to solve that problem, you can run a Fisher's exact test, and for it does not require that assumption of saying that one of the cells has got a smallest frequency. So for us to run a Fisher, let me move down and then I can, yes, I'm going to run the Fisher's test. The moment you run it, for it doesn't consider that assumption, but the interpretation is the same. I'm still seeing that my p-value is 0.01462, which is less than my level of significance. So I have strong evidence to say that there is a relationship between the color of diamond and the price category. Tomorrow I'll do a recap, or just briefly, but kindly do assignment because my time is up. In case there are further questions, we will ask them. Someone is saying they don't have the script. Check in the materials that I've been sending, but I can resend again. Okay, so is that fine? Have you gotten the concept? They're about to close, so we need to stop. Okay, kindly go through the commands again and see how far you can master the concept and then transfer the knowledge in your work. Somebody's asking, how do we save in the console? You can't save the work in the console. You can either save in the R Studio, or if you want to see everything, we talked about R Markdown, can support you to keep all the concepts in one place. Thank you so much. Have a great afternoon. Bye-bye.
I have sent the data set salary in Excel format, and I also sent the one for CSV format. So have a nice day. See you tomorrow. Bye-bye. I'm going to leave. The final script, share with them the final script.